But the same physical state might be minus u. Maybe we've turned by 2 t's, and indeed we have, because in order to get this the way we want it, we have to have the 2 t's in succession. And so it should have been minus u that we multiplied. In other words, we have minus the trace of the propagator. The kind of a circle that I mean here is that 2 particles are coming out in some state and coming back in the same state. I can represent that, if my pants don't fall down, by a belt of this kind, where this one went around one way and this went around the other way. But you see that that is 2 time reversals. It's a 360-degree rotation. And so when there's an odd number of pairs of t's, I count that as 1, tt, okay, an odd number of 360s, the contribution should be positive. That's the case I want. And when there's an even number of tt's, there's extra tt in it, the contribution should be negative because the extra tt makes it negative. This signs plus and minus are relative to what happens with the Bose case, in which they're always positive. So what we have discovered is that we have to put a minus sign in front of the traces of the propagators for the spin-a-half particle, and therefore that produces, as indicated before, a minus sign between 2 diagrams. I think I have another picture of those where you have 2 loops or 1 loop, and the minus sign comes twice with one case and once with the other. When you exchange something connected with 2 loops, it becomes 1 loop. Mr. Finkelstein, David Finkelstein, always makes the following demonstration, which bothered me for a long time because it sounded like it was very important, but I couldn't get all the signs right and straighten it out. But suppose you have 2 loops. I can't make it out of one belt, but you imagine the other one here. And instead of connecting them that way, I connect them crosswise. You see here, this goes over to the other loop, and this loop comes over to this side. Right? And you put them together. How many turns do we have? Okay. Well, you see there's an extra one in there. The loop I wanted went around straight. That's the plus one. If it has an extra turn, it's minus. And so this one's minus to what you would have expected. And that's the reason for the sign change when you exchange the particles. If you want to understand that it really is 2 turns, you try to get, if I can ever get it back to where it was. Yeah, well, here's the way it was on my arm, I think. And you see that if you go around once, twice, you see. T, 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 which is 4. And there's 2 extra t's, and there's a minus sign. So everything's okay, and I think I understand Mr. Finkelstein's demonstration now. Finally, I would like to show you an example in which we have a spin-a-half object in which we know where the angular momentum comes from. And that's fun. Suppose that we had a thing that Dirac invented, and it's therefore appropriate in this lecture, a magnetic pole. And suppose we have a charge Q, and we'll suppose that these particles, the magnetic pole and the charge, are both spin 0. So we don't have to worry about any intrinsic angular momentum of either of those 2 things. But they're in each other's presence. And here's the magnetic pole, and here's the charge, and there's springs from one magnetic field in all directions, and from the other electric field in all directions, and they cross each other and make a pointing vector, which is momentum, which goes around this way, and sure enough, the thing has angular momentum. And the angular momentum is independent of how far apart they are, because if you started this way and moved them in and out, there are no forces, so there's no angular momentum. And you can figure out what the angular momentum is very many ways. And I'll leave as an exercise this. Suppose that it's along the axis. I'm going to show that it's E mu. Q mu. Q is the charge and mu is the thing. By this, suppose you try, here's the magnetic pole and here's the charge. Suppose you want to move that axis. If you move that axis, you've got to move the charge through a magnetic field at a certain velocity, yeah? And that produces a sideways force, which produces a torque, And then you multiply by the time interval, and that gives you the change in angular momentum. And that turns out to be just the change in the direction times e mu. So the angular momentum is e mu, and I'll let you prove it. I wrote EQ. That's very wrong. I changed my charge. Gee whiz, that's horrifying. It should be Q. Okay, the charge is Q, and the pole is mu, and the angular momentum is mu Q. And I got it right here, except to here. I also have another way of checking that the angular momentum, if we choose E mu equal to half h, we can have a quantum mechanical system. Dirac showed no other, only multiples of that are allowed. We'll take the smallest one. There can't be any other value because angular momentum has to be quantized in quantum mechanics. And so there has to be a relation of the pole and the charge. But it's kind of fun to test out whether rotating 360 degrees changes the sign. Imagine this is the magnetic pole, and there's a kind of a needle that goes out for miles. This is where the pole is, and here's the charge, and I'm going to take this little dion, the charge and the pole, and turn it all the way around and see what happens. Well, when you carry a charge through a magnetic field, the phase changes by e to the I times the charge times the line integral of the vector potential. It's a famous theorem. Now, if we carry that thing, that's supposed to intimidate you. That's Bowman, Aharonhof made a lot of that. Now, if we carry this charge all the way around the circle, we have the line integral of A around the circle. And the line integral of A around the circle is the flux. There's some kind of theorem, you know. Integrate A is the curl of over the surface, blah, blah, blah. It's the flux. Now, what is the flux? If I take the positive cap here, it's half the flux that springs out of mu, because the other half goes down. Springing out of mu, the flux is 4 pi mu. No, mu over r squared times 4 pi r squared is the flux, so it's 4 pi mu. So it's half of 4 pi mu. So e to the iq times the flux is e to the iq 4 pi mu over 2. And if I did it right, it's e to the 2 pi mu q, but mu q is a half. It's e to the I pi, which is minus 1. In other words, sure enough, if you rotate it 360 degrees, it's minus 1. It's a spin-a-half object, no problem. It's absolutely right. By the way, incidentally, the reason why it has to be quantized is if I had taken the flux below, I should get the same answer. Right? No reason. How do I know where to take the flux? One is positive and another negative. So I could have gotten e to the minus I pi, which would be different. Oh, no, it's not. It's the same. E to the minus I pi is minus 1 also, so it's the same. And that's why you can quantize it that way. Now, imagine two of these things. One charge and pole, which I'll call A, charge and pole, which I'll call B, and exchange them. Nothing should happen because the charges don't do anything and the poles don't do anything because they're spin zero. Yet the things have angular momentum of half. What happens? What happens? Well, watch. As you carry this B around an A, think of it relatively. The charge on B is moving relative to the charge on A. So if A were kept still to look for the relation, you'd see B would move around to the other side. I mean, relatively. They'd go like that, right? It starts over here and it ends over there, but I don't want to move this, so I just do that to picture it. So we find A going around, the charge going around this way. Meantime, back on the farm, the other one, its charge is moving around B. So if B is held fixed, you find that charge A is going around B in this direction. And so there's a phase change, which is the integral of the charge, e to the I QA, you know, the line integral of the vector potential from here to here, and an additional phase change from the other one, which is the line integral from there to there. No matter what the shape of this line is, after a little thought, this line is a kind of mirror of it, of course, right? And therefore you're going around something which splits the space 50-50, and the line integral all the way around is again the flux, and we found out the flux was minus 1, half flux, half flux. And so you get from these phase shifts, from the mechanical efforts of the charges moving through the poles, an extra factor -1. And so when you compare what you get straight and what you get when you move them, you have to multiply by -1. In other words, this time we discover that this time the sign comes from the fact that when you exchange two things, one relative to the other, plus vice versa, has a 360-degree rotation in it. It goes around, altogether. Charges are moving 360 degrees around each other. And then it works. And so I would like to summarize the whole thing by saying, when two charges are exchanged, there's an implicit rotation of 360 degrees. We have noticed it inside with those productions and so on in terms of the T's and stuff when we recross it. But when you exchange two charges, there's effectively somewhere hidden in there, if you analyze it carefully, a 360-degree rotation. And it's this. If the spin is a half, then the amplitude must be changed by a factor -1 because of that 360-degree rotation. This experiment was to show the extra twist, which I already did for you. And that's the key to the factor of -1 that comes in the exchange of fermions relative to what happens in bosons. But to summarize it, although we went a long distance into detail, it's interesting to remember what we did, because it's not much. If you suppose there's only particles and things can only go forward, you find yourself impossible to avoid going into the outside the light cone. This cannot be for only positive time, because it depends on coordinate system. So therefore there must be something outside the light cone for the negative times too. And therefore the path that went forward from a different point of view has to go backward, and we find pair production. Then when we took a very simple example of a charge, all we had to do to discover that there's hidden in this works, when you go to put it together, the keys to spin and statistics is in considering in this diagram, that when you're calculating the sum of the probabilities, that this diagram has to be an effect. In order for this to be here, you have to have an effect on the probability of producing a pair that depends upon whether another charge is present. An answer which comes out positive for bosons and negative for fermions. And it comes out negative for fermions because fermion has got a kind of a linear term in the propagator, and the linear term changes sign relative to this as you flip over, and so there's a minus sign. That contains everything, and the rest of it was just elaboration. Thank you very much.
I call on Professor John Taylor to propose a vote of thanks.
I can imagine a history of science examination question about the end of this century saying compare and contrast Dirac and Feynman, and he's given us some scope for beginning to answer that question today. The work of Dirac and Feynman has been interrelated in the most extraordinary way. And Feynman has given us today a talk which beautifully shows a lot of these key points which these two men have worked on. He's come over 9 time zones, I think, to give us this lecture, and will presumably return over 9 time zones. And I hope there isn't a minus sign in that. We're very grateful to him for coming. Thank you very much.